In this video, I'm going to cover forepropagation in a convolutional layer. In previous episodes, I covered forepropagation and backpropagation in neural networks with dense layers. These layers work with every input connected to every output. This allows for a huge range of functionality, but becomes very expensive to compute at larger sizes. Convolutional layers are an optimization to massively improve performance. A dense layer would need to train its weights and biases to learn that spatially close inputs are more significantly correlated. Spatially close inputs might be pixels in an image that are close together. In convolutional layers, this comes as standard, embedded in how they operate. Convolutional layers can be used for tasks like image recognition, where we can reduce spatial regions to abstract components. Dense layers are the fundamental operation, while convolutional layers are an optimization. They are a hack using human intuition. Convolutional forepropagation has four components: the input, the output, the filter, sometimes referred to as the kernel, and the bias. The operation moves the filter across the input to produce each value in the output. For each output value, it multiplies every value in the input by the respective value in the filter, sums these values, then adds the bias. As the filter grows in size, it will reduce the impact that values on the edges of the input can have on the output. Through multiple layers, this will imply an implicit weighting in favor of values closer to the center of the input. To counteract this, we can apply zero padding to the input. Zero padding involves adding zero values to the edges of the input such that the output is the same size as the non-padded input. To handle more complex data, convolutional layers can incorporate additional components. The first additional component is channels. These represent an additional dimension in the input. This can be used to handle RGB channels in an image. The second additional component is allowing a variable number of filters. Different filters can be used to search for different elements in an input. In an image, one filter may search for vertical lines, while another may search for horizontal lines. In practice, in real models, these elements are unlikely to be so simple. They are likely to be very abstract, and it will often be difficult to make any meaningful inferences about what they represent. Two topics I've missed in this video are variable stride and variable dilation. It is likely you will come across these when using a neural network. They are not more notably complex than anything I've covered in this video. They are just another optimization applying human intuition. I've excluded them for the sake of brevity. If you were able to follow along with this video, you should now have a fundamental grasp of forepropagation with convolutional layers.